All right, Newton's law of cooling. We in this lesson we're going to look at some applications where real life situations where logarithms are used, and like it says right on your paper there are many real world applications where exponential and logarithmic functions are used. The magnitude of earthquakes measured on the Richter scale, formula M equals log of L over S. In chemistry, pH is used to measure the acidity of a compound. pH equals negative log H3O plus. Okay, so we have seen financial applications already. Population growth, we've done that. So there are many different areas where logarithms are useful. Another one is called Newton's law of cooling. So think about this situation. You take something out of an oven, or you take a pan off the stove, or you have a hot cup of coffee, hot chocolate or something, right? That's a good example. You have a hot chocolate, right? Cup of hot chocolate, and just poured it, set it down. Now the room temperature is only 70 degrees, 68 degrees, whatever. Eventually, that hot chocolate is going to cool down to the room temperature, right? If you're outside and it's 20 degrees, you take that hot chocolate outside, it's going to cool down even faster based on the surrounding temperature. Okay, that surrounding temperature we're going to call the ambient temperature. So you see ambient temperature, which can be represented by T of A. That's going to be the surrounding temperature, the temperature of the room or the temperature of the outside, wherever you're at. But this is Newton's law of cooling right here. So this right here, Newton's law of cooling. It looks like a bunch of stuff. You're probably like, whoa, what the heck is this? It's not bad. You don't have to memorize it, but you will have to know how to use it and have to interpret it and understand how what variables represent what everything represents. So basically they tell you, and if you get something like this on your exam, they're going to let you know what everything represents. But this right here is kind of telling you that. T of T is the temperature of the object after a certain period of time. That's the function. TA we said was the ambient temperature. That's the temperature of surroundings. That's here and here. T sub 0 is the initial temperature of the object. That's what starts at. So you take that pan out of the oven. If you were cooking at 400 degrees, that pan is 400 degrees, right? You take it out, you're putting it into a 70 degree surrounding. K is the constant, the rate, basically. Remember how we used to call the rate R? We're going to call it K now. So remember we used to have E to the RT, E to the RT. Okay, so now it's E to the KT. All right, so we just got to get used to that. All right, so now a pan is removed from a hot oven that has been baking cookies. Sorry, I read that wrong. A pan is removed from a hot oven that has been baking cookies at a temperature of 350 degrees Fahrenheit. The room temperature is 70 degrees Fahrenheit. The pan is made of materials that will cool 27% per minute in a room temperature. Write an exponential function. So here's your exponential function right here. Okay, T sub T, T of T equals, now TA is my ambient temperature. That's the temperature of the room, 70 degrees, so 70, okay, plus T sub 0 is that initial temperature. We took that pan out of the oven at 350 degrees, so that's going to be 350. And then, what did I do? Sorry about that. Didn't want to close the parenthesis off. 350 minus the ambient temperature again, 70. And times E raised to the negative KT. Negative K, 27%, so 0.27. And then T. Function of time. T is time. Okay, so there's my exponential function. Of course, I would simplify that, so I'm going to write it as T. To go to my red here. So it's going to be T sub T equals, now 350 minus 70, of course, is 280. So we're going to write it as 70 plus 280 e to the negative 0.27 t. So notice how it is just an exponential function, right? How hot is the pan 2 minutes after being removed? Well, they're giving us the time. So we're going to plug 2 in for t. That's the same thing as saying t of 2. T of 2. T of 2 equals, so it'll be 70 plus 280 e to the 0.27 times 2. And, e to that first, then times 280, then 70. I already did it ahead of time just to save time on your video here. It'll be 233 degrees. So as you can see, the pan's cooling down. It started at 350 degrees. Now it's down after 2 minutes. It's down to 233 degrees. Now they want you to find, to the nearest hundredth, how long until the temperature drops to 150. So now they're giving you the temperature at the end of a time period, but we don't know what the time period is. So that's the T of T. The T of T is 150, the time at the end of the time period. So we're going to go, I got a new software here on this thing, so I'm trying to get it to, it's a little weird if it looks a little different to you. We got purple now, though. It's cute. 150 is what we want. That's our desired amount. 70 plus 280 e to the negative 0.27 t. Oh, I just noticed that it should be a negative up here. Anybody else notice that? Probably not, right? All right, negative 0.27 t. Now, we're solving for t, and of course, t is in the exponent, so you know we're going to need logs, all right? A little bit different. Remember, we normally divide out first, but see how you have this plus going on here? So what we're going to need to do first is subtract the 70. So a little bit different than our population growth or anything else we've done. 80 equals 280 e to the negative 0.27 t. Okay, so now it looks kind of like what we've done before. Where remember how we want our investment to triple, our investment to double, and then you'd have to divide it out. Same thing now. Divide out that 280. Okay, so we're going to have 80 over 280. Negative 1 point. Oh, I'm sorry. That's not right. I'm going to leave it as 80 over 280. I'm going to leave it as 80 over 280. You could divide it out. I didn't divide it out. 80 over 280 equals e to the negative 0.27 t. Let me grab a calculator real quick, do that. 80 over 280. I thought I did it. Okay, 0.2857 or so. The problem is when you divide it out, you get 0.2857142857. So I'm actually going to leave it as this, okay, because I know that my natural log is going to be a base e anyways. So we're going to do natural log of both sides here because it's base e. So natural log of 80 over 280. So we'll do this a little bit differently. And then it's going to be negative 0.27 t natural log of e. See? That exponent comes in front of the log. Natural log of e is just 1. Okay, so that goes away. Now I can just say, all right, negative divide by negative 0.27. This is kind of a shortcut you're going to be able to do for these. All right, and of course, my final answer is going to be 4.64. Nearest hundredth. So it will take 4.64 minutes to get down to 150 degrees Fahrenheit. Still pretty hot, right? And then eventually it's going to get down to our room temperature of 70 degrees. Okay? So we're just going to do one more here. One more example, and then we're going to finish up in class because we have 2 days to work on this. And we're going to do a few more examples in class. So example 2 here. Similar function. They're giving us a function, and what we have to realize here, I'm going to write the original function, t of t, f of t. Let's call it f of t, right? F of t, because they're calling it f of t, equals, okay, so then it's t a plus t0 minus ta e to the negative kt. Okay, so that is our regular Newton's law of cooling, since we're talking about cooling here. Notice how they only have this and the plus 68s listed after. They're going to do that. Sometimes they're going to put it at the end. It doesn't matter. Obviously, this here, this plus t sub a, that could be at the end. I could go plus t sub a, right? And then just not put it there. So this example is meant to show you that sometimes they'll make it a little bit different. You got to just pay attention. Also, see this is already done for you. See the E, you got the rate, the T there, right? Here's the rate, the K is obviously negative 0.08. And then, but this number here, this T0 minus TA, it's 112. So keep that in mind. Now, what is the temperature of the room? Well, the temperature of the room is the 68. That's the TA. That's the ambient temperature. So that's easy. That's an easy one. Then it says, what is the temperature of the coffee at the beginning of the experiment? Don't say, oh, it's 112. Okay, not necessarily 112. Because, remember, the initial cup was right here, T of 0. Okay, so T sub 0 minus the ambient temperature, that came out to be 112. See? This number here is 112. So T0 minus TA is 112. We already know T sub A is 68. So T sub 0 minus 68 is 112. Okay? T sub 0 minus TA minus 68 is 112. Okay? Now add 68. T sub 0 is 112 plus 68. So T sub 0 is actually 180 degrees. The initial temperature was 180 because it was already done for you. See, it's got the 112. It was already done for you. What will the temperature of the coffee be after cooling for 2 minutes? All right, that's just plugging in a 2, right? So we're going to do f of 2. And that's going to be 112 e to the negative 0.08 times 2 plus 68. And that comes out to be, I did it already for you, 163 degrees. So started at 180, went down to 163. After how many minutes will it get to 140? So 140 is my f of x now. 140 equals 112 e to the negative 0.08 t. So again, just like our last example, okay, 140 minus 68, so we got 72 equals 112 e to the negative 0.08 t. Okay, divide by 112. Now let's see if we can use our shortcut. Natural log of 72 over 112 equals negative 0.08 t. So then divide by negative 0.08. So you do this, and then you divide by negative 0.8. The t is going to be 5.523. If you got a calculator, you can check that out. 5.523. So that's how many minutes it's going to take to get down to 140 degrees. What is the temperature of the coffee after 3 hours have elapsed? 3 hours, guys, is 180 minutes. So now we do f of 180. You could almost do this with common sense. How long? I mean, you're talking about a cup of coffee sitting at room temperature for 3 hours. And the room temperature is 68. Guess what's going to happen to that cup of coffee after 3 hours? It's going to be room temperature, okay? So this is going to be 68 degrees. I don't even have to do it. I know it's going to be 68 degrees. If you want to do it, you put the 68 in for the tea, and you could tell that, well, obviously, I mean, you put the 180 in for tea, and you tell it's going to be 68, okay? So, anyways, Newton's law of cooling also works with heating. So you'll see some of that in our lesson, but we're going to spend a day, or so just doing some more examples, getting a little bit more familiar with it, and then we'll get some practice on it in the next few days. All right? Take care. See you then.